Welcome to White Space. How big is IC 1101, the largest galaxy we've ever found, really? Put this on in the background, close your eyes if you want, and let the story carry you. Look up at the night sky long enough and you begin to understand that the universe does not care about scale the way we do. What appears as a faint smear of light to the naked eye might contain more stars than grains of sand on every beach on Earth. The structures that house those stars, galaxies, are so enormous that we don't measure them in kilometers or miles. We measure them in years of light. Years of travel at the fastest speed the universe permits. And still, some galaxies are so large that even light takes millions of years just to cross them. We tend to treat scale as something we can eventually absorb. We are taught to imagine the Earth as a marble, the Sun as a basketball, the solar system spread across a football field. These models are useful in the way that maps are useful. They preserve relationships while discarding true proportion. But at galactic scales, even the most generous model starts to fail. The distances between stars within a single galaxy are already beyond comfortable visualization. The distances between galaxies defeat it entirely. And the distances between galaxy clusters, the vast gravitational cities in which individual galaxies congregate, operate in a register so removed from human experience that the numbers begin to function more like poetry than measurement. There is a useful exercise that astronomers sometimes describe to students trying to feel the scale of the cosmos. Take a grain of sand. Hold it at arm's length against the darkest patch of sky you can find. The area of sky covered by that grain of sand contains, within the depth of the observable universe, something like 10,000 galaxies. Not 10, not 100, 10,000. Each of those galaxies contains hundreds of billions of stars. Each of those stars may have planets, and the grain of sand covers only a tiny fraction of the sky. Multiply that across the full sphere of observation, and the numbers become not just large, but practically meaningless. Beyond the reach of intuition, beyond the reach of analogy, approachable only through mathematics. The universe is not merely large. It is large in a way that resists comprehension as a matter of principle. We belong to one such structure. The Milky Way stretches roughly 100,000 light-years from edge to edge. A vast disk of several 100 billion stars rotating slowly around a central black hole. For most of human history, we assumed it was the whole of creation. It is not even close. Among the 2 trillion or so galaxies we now believe populate the observable universe, our galaxy is, in the grand scheme of things, unremarkable. It is average in size, average in age, and average in brightness. It does not anchor the center of its cluster. It is not the brightest object in its region. It is one of dozens of galaxies loosely bound together in what we call the local group, which is itself a relatively modest collection compared to the great clusters and superclusters that dominate other parts of the cosmic map. The local group is in turn part of the Virgo supercluster, which is one of roughly 10 million superclusters distributed across the observable universe. We are not at the center of any of these structures. We sit on the periphery of an unremarkable spiral arm, in an unremarkable galaxy, in an unremarkable corner of a supercluster that is itself unremarkable by the standards of the cosmos. Somewhere out there, separated from us by more than 1 billion light-years, sits a structure that makes the Milky Way look like a neighborhood compared to a continent. That structure is IC 1101, and it is the largest galaxy we have ever found. IC 1101 lies 1.04 billion light-years away in the direction of the constellation Virgo, though its outer regions bleed across neighboring patches of sky. It anchors the center of a massive galaxy cluster called Abell 2029, and it dominates that cluster the way a sun dominates a solar system, outshining everything around it. The Abell 2029 cluster is itself an enormous structure, containing hundreds of galaxies spread across tens of millions of light-years. It was catalogued in 1958 by the American astronomer George Abell as part of his systematic survey of rich galaxy clusters visible in photographic sky surveys, a catalogue that remains one of the foundational references in observational cosmology. Abell 2029 is classified as a rich regular cluster, meaning it is gravitationally settled, relatively symmetrical in its distribution of mass, and dominated by a single central galaxy rather than a collection of competing bright members. That central galaxy is IC 1101. It sits at its gravitational heart, having accumulated matter from its surroundings over billions of years. The other galaxies in the cluster orbit around it, are pulled toward it, and in some cases have already been absorbed into it. Despite the staggering distance between us and IC 1101, it registers at an apparent magnitude of around 14.7, a testament to the sheer volume of stellar energy it radiates. Objects far closer to us are harder to see with a basic telescope. This one, more than 1 billion light-years away, is detectable because it is so extraordinarily bright. To put its size in concrete terms, the Milky Way spans about 100,000 light-years. IC 1101 spans approximately 6 million. That is not a modest enlargement. That is a difference so profound it barely fits inside the imagination. If you placed IC 101 where the Milky Way sits, it would engulf not just our galaxy but also Andromeda, the Triangulum galaxy, and every other member of our local group with room to spare. It would reach past the nearest galaxy clusters and begin to encroach on others. The star count within this colossus reaches an estimated 100 trillion, roughly 500 times the stellar population of our own galaxy. It is a number that loses meaning the moment you speak it. 1 trillion is already beyond intuitive grasp. 100 trillion is simply larger than the mind was built to hold. What is more graspable is the consequence. In a universe full of extraordinarily large things, IC 1101 is in a category largely by itself. Even its mass tells only part of the story. Like all galaxies, IC 1101 contains far more matter than can be accounted for by its visible stars alone. The stars, gas and dust we can observe are embedded in an enormous halo of dark matter, a form of matter that interacts gravitationally, but emits no light and cannot be directly detected. Dark matter halos typically extend far beyond the visible boundaries of a galaxy, often to distances several times the optical diameter. For IC 1101, this means the total gravitational reach of the system, the true extent of its influence over surrounding space, is substantially larger than even the 6 million light-year figure suggests. The visible galaxy is, in a sense, the luminous tip of a far larger invisible structure. When astronomers study galaxy clusters like Abell 2029, they often measure the total mass of the cluster by observing the X-ray emission from hot intergalactic gas that permeates the cluster space, or by measuring how the cluster's gravity bends the light of background objects through gravitational lensing. Both methods reveal that the visible matter, the stars and gas we can see, accounts for only a fraction of the total mass. The rest is dark matter, distributed in enormous halos around and between the member galaxies, with the largest concentration centered on IC 1101 itself. The age and color of IC 1101 tell a particular story. The galaxy glows with a yellowish tint, a signature of old metal-rich stars that have already burned through the energetic blue phase of their youth. Young stars burn hot and fast, radiating in the blue and white part of the spectrum. As they age, they cool and redden. A galaxy dominated by yellow and orange light is a galaxy whose stellar population has matured, a galaxy that has not formed significant numbers of new stars in a very long time, and whose existing stars are well into the second half of their lives. The stars dominating IC 1011 are estimated to be 7 to 8 billion years older than our Sun. Our Sun formed about 4.5 billion years ago. That means the stellar generations inside IC 101 trace their origins back to within a few billion years of the Big Bang itself, to the earliest age of star formation in the universe, to a time when the cosmos was so different from what it is today that the two epochs barely seem like the same universe. Based on this, astronomers estimate the galaxy to be roughly 11 billion years old, though confirming this precisely remains a challenge given the distance and complexity involved. What we can say with confidence is that IC 1101 is ancient. It has been accumulating stars and mass since the universe was young, and the record of that accumulation is written across its spectrum. The term metal-rich in the language of astronomy carries a specific meaning that differs from everyday usage. To an astronomer, metals are all elements heavier than hydrogen and helium. The universe began with essentially only those two lightest elements. Every heavier element, carbon, oxygen, iron, silicon, the full periodic table beyond helium, was forged inside stars through nuclear fusion and released into the interstellar medium when those stars died. The first generation of stars formed from the primordial hydrogen and helium of the early universe contained no metals at all. Each subsequent generation of stars inherited the chemical enrichment produced by all prior generations. A metal-rich stellar population is therefore also an old stellar population, one that has been through many cycles of stellar birth and death, accumulating heavy elements across billions of years. The yellow glow of IC 1101 is not just a color, it is a record of deep time. It tells us that the stars in this galaxy have been living, dying, and chemically enriching their surroundings since the cosmos was less than 1 billion years old. Because IC 1101 contains so few nebulae, the cold, dense clouds of gas and dust where new stars are born, its internal landscape is different from younger, more active galaxies. In the Milky Way, star-forming regions glow with ionized gas and the fierce ultraviolet light of newborn stars. Vast molecular clouds, some spanning hundreds of light years, are collapsing in slow motion into stellar nurseries that will ignite over the next several million years. In IC Luglev 1, those features are rare. The molecular gas that once fueled such activity has been largely exhausted. What dominates instead is the combined aging glow of 100 trillion mature suns, distributed across a volume so large that even at the edge of the galaxy, starlight would fill the sky in ways that no world in our own galaxy experiences. There would be no dark sky, there would be no night. In the sense we understand it, any planet at the outskirts of IC 1101 would orbit its star under a sky permanently illuminated by the integrated light of trillions of other stars, a sky more like a diffuse, all-encompassing glow than the scattered points we see from Earth. One of the more provocative conversations surrounding IC 1101 involves the question of life. With 100 trillion stars and presumably a proportional number of planets, the raw statistical argument for inhabited worlds within this galaxy is compelling. No other single galaxy offers more chances. Sheer number favors complexity. And complexity favors the emergence of biology, and biology, given time and stability, tends toward increasing organization. If the logic that produced life on Earth is not unique to Earth, then IC 111, with its staggering inventory of worlds, is the most probable address in the known universe for the existence of other minds. But probability is not the same as likelihood. And the same features that make IC 1101 statistically fertile also make it environmentally severe. The internal environment of IC 101 is extreme. Stellar densities in the core are so high that stars pass close to one another far more frequently than in the Milky Way. In our own galaxy, the nearest star to our Sun is more than 4 light years away, a distance so large that even if both stars had planets, the gravitational interaction between them would be essentially negligible. In the densely packed regions of IC 111, stars would be significantly closer on average, and the gravitational and radiative effects of neighboring stars would be far more disruptive to the orbital stability of planetary systems. Planets could be gravitationally perturbed out of stable orbits. The repeated near passages of other stars could strip planetary atmospheres over long time scales. Radiation fields from the concentrated stellar population and from the intensely active galactic nucleus would bathe interior regions in energetic particles and X-rays at levels that would challenge the persistence of surface biology. Astronomers studying the habitability of galaxies have developed the concept of a galactic habitable zone, a region within a galaxy where the conditions for life are most favorable, defined broadly by distance from the galactic center, chemical enrichment from previous stellar generations, and exposure to disruptive radiation. In the Milky Way, this zone is thought to lie at intermediate radii, far enough from the dangerous central regions to avoid excessive radiation and gravitational disruption, but close enough to benefit from the chemical enrichment that makes rocky planets and biochemistry possible. In IC 1101, the equivalent calculation becomes considerably more complicated. The entire galaxy is old and chemically enriched, which is favorable, but the stellar density is extreme across a far larger volume, which is not. If a habitable zone exists within IC 1001, it likely sits in the outer regions of the galaxy, where stellar encounters are less frequent and radiation levels are lower. Outer regions also tend to have fewer heavy elements, which might limit the complexity of chemistry available. Whether those conditions have ever combined in the right way, in the right place, at the right time, across the vast history of this galaxy, is a question we cannot answer. And there is another peculiarity. The interior of IC 101 is so overwhelmingly bright, so densely packed with starlight from every direction, that any civilization forming deep within it might look outward and see nothing beyond its own galaxy. The light from within would drown out the light from without. The rest of the universe, including every other galaxy, every quasar, every cosmic filament beyond, could be effectively invisible to them. The concept of extragalactic space might never develop. The idea that other galaxies exist, that the universe extends beyond the boundary of their own stellar system, might be permanently inaccessible. Not because the knowledge is too difficult to obtain, but because the observational evidence is too thoroughly obscured. They might spend their entire existence believing their galaxy was the totality of all things. Every philosophical tradition, every cosmological framework, every map of the universe they constructed would begin and end with IC 1101. The most advanced observatories they could build, pointed in any direction, would return only the light of their own stars reflected and multiplied by distance. The window onto the larger cosmos that we take for granted, that our clear dark skies make possible, would simply not exist for them. Given the scale they would be born into, the error would be forgivable. The universe they knew would still be larger than anything we have ever observed. IC 1101 was not always known for what it is, like many of the deepest features of the universe. It was first mistaken for something much smaller and much closer. In 1790, the British-German astronomer William Herschel, one of the most prolific observers in the history of astronomy, the man who discovered Uranus and catalogued thousands of nebulae, observed a faint smudge in the sky and recorded it as a nebula, a cloud of gas within the boundaries of the Milky Way. Herschel was an extraordinarily systematic observer who surveyed the sky with mirrors he ground himself, working through the night for decades to catalogue over 2,000 objects. His survey methods were rigorous by the standards of his time, but the true nature of those faint smudges was simply beyond the resolving power of his instruments and beyond the conceptual framework of his era. The idea that some of those smudges might be entire star systems comparable to or vastly larger than the Milky Way was not seriously entertained. IC 1101 sat in records as an unremarkable curiosity for more than a century. In 1895, John Louis Emile Dreyer compiled his index catalogue of nebulae and star clusters, and the object became the 11131st entry. The name was purely administrative. The object itself remained poorly understood. The same confusion surrounded many of these distant objects in the late 19th and early 20th centuries. The sky contained hundreds of these faint, diffuse patches, some clearly gaseous, others displaying faint spiral or elliptical structure. What they were was genuinely unknown. Some astronomers maintained that all of them were features of the Milky Way, local gas clouds, young star clusters, or star-forming regions at various distances within our own galaxy. Others looked at the spiral structures and suspected something more. The debate crystallized in 1920 into what became known as the Great Debate, held at the Smithsonian Museum of Natural History in Washington, where astronomer Heber Curtis publicly argued that objects like Messier 31, the large spiral in Andromeda, were not features of the Milky Way at all, but independent star systems separated from us by distances previously thought impossible. His opponent, Harlow Shapley, held that the Milky Way was far larger than commonly assumed, and that these objects were embedded within it. Both men made strong arguments. Both men were right about some things and wrong about others. The argument was not resolved that night. It was resolved 5 years later by Edwin Hubble. Working with photographic plates from the Mount Wilson Observatory in California, where the 100-inch Hooker telescope was then the most powerful instrument in the world, Hubble identified Cepheid variable stars in images of Messier 31. Cepheid variables are stars that pulsate, expanding and contracting in regular cycles, with the period of their pulsation directly related to their intrinsic luminosity. This relationship, first identified by astronomer Henrietta Swan Leavitt in 1908, makes Cepheids reliable distance markers. Measure the period of the pulsation, determine the intrinsic brightness, compare to the observed brightness, and calculate the distance. The distance Hubble measured to the Cepheids in Messier 31 was roughly 1 million light-years, well beyond the outer edge of even the most generous estimates for the Milky Way. Messier 31 was a separate galaxy. Hubble published his full findings in 1929, and the implications cascaded through astronomy. Not only did other galaxies exist, they existed in enormous numbers. The universe was far larger and far more richly structured than anyone had seriously imagined. IC 1101 was confirmed to be extragalactic in the early 1930s, recognized as a distant, independent system of stars rather than a local gas cloud. But its true dimensions remained unknown. The technology to resolve its outer structure in any detail did not yet exist. It was not until 1995, the same year the Hubble Space Telescope produced its landmark deep field image, revealing thousands of galaxies in a patch of sky roughly the size of a grain of sand held at arm's length, that astronomers began capturing IC 1101 with enough resolution to appreciate its actual scale. The deep field image itself was a turning point in cosmology, demonstrating in a single photograph that even the apparently empty regions of the sky are in fact filled with galaxies extending to the edge of the observable universe. It was a demonstration that the universe is not only large in the sense that the nearest galaxy is far away, but large in the sense that there is simply no end to the depth of it. Ish Leun, resolved in that same era of improved imaging, claimed its title as the largest of them all. It has held that title ever since. The question that followed was inevitable. How does something get this big? The formation of galaxies is not fully understood, but the broad outlines are reasonably well established. In the earliest moments after the Big Bang, the universe was not uniform. There were slight variations in density, regions slightly more packed with matter than others, imprinted during the inflationary epoch. The period of extraordinarily rapid expansion that occurred in the first fraction of a second of cosmic time. These density variations were tiny, at the level of 1 part in 100,000, detectable today in the faint temperature variations of the cosmic microwave background, the afterglow of the Big Bang, still observable as a uniform glow of microwave radiation filling the sky in every direction. Those variations were enough. Gravity amplified them over hundreds of millions of years. The denser regions pulled matter inward from their surroundings. But in the early universe, the matter pulling inward was not primarily the hydrogen and helium gas we associate with visible stars. It was dark matter, the invisible gravitationally active component that makes up the majority of the universe's total matter content. Dark matter began clustering first, forming the gravitational scaffolding, the dark matter halos, into which ordinary matter later fell. Hydrogen and helium gas streamed along the filaments and sheets of the cosmic web, a vast three-dimensional structure of dark matter that threads through the universe like a sponge, with great voids between the filaments and dense nodes at their intersections. At those nodes where multiple filaments met and ordinary matter accumulated in the deepest gravitational wells, the conditions for star formation were first reached. Gas clouds collapsed. Where gas accumulated densely enough, it reached conditions sufficient to ignite nuclear fusion. The first stars were born. They were enormous by modern standards, hundreds of times the mass of our sun, and they burned ferociously and briefly before collapsing into the first black holes. Those black holes grew by consuming surrounding gas. They became the gravitational anchors around which the earliest proto-galaxies assembled. These proto-galaxies were small by modern standards, loose, irregular assemblies of stars with no well-defined structure, held together more by proximity and shared gravitational well than by any organized rotation. But they were not alone. The same dark matter scaffolding that drew them into existence continued to pull them toward each other. Over hundreds of millions of years, these small structures found each other, fell together, and merged. Each merger produced a more massive system. Each more massive system attracted more gas, formed more stars, and became a stronger gravitational anchor for the next round of mergers. The universe's history of galaxy formation is essentially a history of this hierarchical accumulation, small things combining into larger things over and over across cosmic time. The process begins with dwarf galaxies, the smallest and most primitive galactic structures, containing anywhere from a few million to a few 100 million stars and spanning only a few thousand light years. Dwarf galaxies are not relics of the early universe alone. They continue to form and they continue to exist in large numbers today, often in the gravitational company of larger galaxies. The Milky Way has several dozen dwarf galaxies orbiting it. Some of these companions, the Magellanic Clouds being the most famous, are still sufficiently intact to be visible to the naked eye from the southern hemisphere. Others have been stretched and disrupted by tidal forces into long stellar streams that wrap around the Milky Way, visible only through careful survey observations. They are in the process of being consumed, their stars gradually incorporated into our galaxy's outer halo. This is not a violent process. It is slow, patient, and inexorable. IC 1101 has been doing the same thing on an incomparably grander scale for 11 billion years. When two dwarf galaxies of comparable size collide, the event unfolds over hundreds of millions of years. Their central black holes do not immediately merge. They orbit each other at decreasing distances, each pass drawing them closer, while streams of stars are flung outward along elongated arcs by the tidal forces involved. The two galaxies lose their individual identities gradually. their stars intermingling, their gas clouds compressing against each other and igniting new star formation. Eventually, the cores spiral together and merge, releasing an enormous burst of gravitational energy in the form of gravitational waves, ripples in spacetime of the kind first directly detected by the LIGO Observatory in 2015, though in that case from the merger of stellar mass black holes rather than the supermassive ones at galactic centers. The combined black hole sits at the center of what is now a more massive, more complex system. Gas clouds from both original galaxies compressed by the collision heat up and collapse into new stars. The structure develops rotation, arms begin to form. A spiral galaxy is being born. The distances between individual stars during these collisions are so immense that direct stellar impacts are extraordinarily rare. Two galaxies can pass completely through each other, and the stars within them will largely miss each other, their paths separated by light years even at their closest approach. The universe is mostly empty space, and the emptiness between stars within a galaxy is almost unimaginable in its depth. What does collide dramatically and consequentially is the gas. Interstellar gas clouds from two galaxies smashing into each other at hundreds of kilometers per second generate shock waves, heating and compressing the gas to the point where gravitational collapse becomes inevitable. The physics that prevents a gas cloud from collapsing under its own gravity, primarily the thermal pressure of the gas pushing outward, is overwhelmed by the compression of the collision. Star formation ignites across the merged structure on a scale that neither galaxy could have achieved alone. The merged system brightens. It grows. It develops the characteristic flattened disk and spiral arms that we associate with mature galaxies. Our own Milky Way is a spiral galaxy, as is our nearest large neighbor, Andromeda. They are not static. Both are moving. They have been moving toward each other since long before the Sun existed, drawn together by mutual gravitational attraction across the 2.5 million light-years that currently separates them. At present, Andromeda is approaching us at roughly 110 kilometers per second. In roughly 4 billion years, the two galaxies will make their first close pass. The encounter will not result in an immediate merger. The galaxies will pass through each other separate and then fall back together over hundreds of millions of years, making several passes before finally combining. Throughout this process, new stars will form in enormous quantities from compressed gas clouds. The night sky for any planets that survive with habitable surfaces will transform beyond recognition. Stars currently invisible to the naked eye will become prominent. New star-forming regions will blaze across the sky. The familiar constellations will be unrecognizable, and eventually, over billions of years, what was two galaxies will become one, larger and older than either of its predecessors. That future galaxy already has a name: Milkdromeda. When spiral galaxies collide, the scale of the event is correspondingly grander. Gas clouds from both galaxies slam together, triggering what astronomers call a starburst, a period of extraordinarily rapid star formation in which millions, sometimes billions, of new stars ignite over a cosmically brief span. The merged core brightens dramatically, sometimes briefly outshining the rest of the galaxy combined. The infrared luminosity of starburst galaxies can exceed 1 trillion times the luminosity of our Sun, enough to be detectable across billions of light years. The arms begin to blur and dissolve as the orbital dynamics of billions of stars are disrupted by the gravitational perturbations of the encounter. Loops and tails of stars extend outward into intergalactic space. The galaxy passes through a phase of dramatic, visually striking distortion, the kind of morphology that appears repeatedly in the most famous images of the Hubble Space Telescope, two galaxies intertwined in slow-motion collision, their spiral arms thrown into arcing bridges. As the combined mass of stars grows denser and the remaining gas reserves thin out, depleted by the starburst and by the consuming appetite of the central black hole, the galaxy loses its spiral structure entirely. The organized rotation that maintained the disk is disrupted. Stars that were once moving in roughly circular orbits in a flat plane now move in a more complex distribution of orbits at various orientations, their average motion forming a roughly ellipsoidal shape. What remains is an elliptical galaxy, smoother, more symmetrical, lacking the organized rotation of a disk galaxy, and dominated by older stars whose blue-white youth has given way to the cooler, yellower light of middle and late life. The gas that once fueled spiraling arms and ongoing star formation has been largely spent. The galaxy is no longer a factory of new stars in any significant sense. It is coasting on what it has already built, its stellar population aging steadily and collectively. IC 1101 is a giant elliptical galaxy, the largest known, and its color and composition indicate it has been in this final structural stage for a long time. It must have undergone an extraordinary number of mergers over the full span of cosmic history, beginning as a relatively modest system in the early universe and growing through collision after collision, absorbing galaxies large and small, accumulating mass that other galaxies in its cluster could not match. The galaxies at the centers of large clusters tend to be the largest and oldest, because they sit at the bottom of the deepest gravitational wells. Matter falls toward them from every direction. Other galaxies fall toward them. Over billions of years, a galaxy at the center of a rich cluster like Abell 2029 becomes a kind of cosmic accumulator, drawing everything within gravitational reach into itself. Astronomers call these objects brightest cluster galaxies, and they represent the endpoint of the hierarchical assembly process, the final product of 1 billion years of mergers. IC 1101 is the most extreme example we have ever found. It is what happens when a galaxy is given 11 billion years, a deep gravitational well, and a cluster full of potential merger partners. That accumulation also implies something about what lies at its center. Every significant galaxy is bound together by a supermassive black hole at its core, and the mass of the central black hole tends to scale with the mass of the galaxy that hosts it. This relationship, known as the M-sigma relation, appears to hold across a wide range of galaxy masses and types, suggesting that the growth of the central black hole and the growth of the galaxy it inhabits are fundamentally linked, feeding back on each other through processes that are still being worked out in detail. For IC 1101, that central black hole is, by any reasonable estimate, enormous. The galaxy's core emits intense radio radiation consistent with an active galactic nucleus, a black hole still actively consuming surrounding material, generating radiation as infalling matter is heated and accelerated in the accretion disk surrounding the event horizon. The physics of accretion disks is well understood in broad outline. As matter spirals inward, it forms a flattened, rotating disk, heating up through friction and compression to temperatures of millions of degrees. The innermost regions of the disk radiate across the full electromagnetic spectrum, from radio waves through X-rays, with a precise spectrum depending on the mass of the black hole and the rate at which it is consuming material. The brightness and radio loudness of IC 101's core are both consistent with a black hole that has grown to extreme mass through billions of years of feeding, and that is still feeding, still growing, though at a slower rate than during the periods of active merger-driven accretion in the galaxy's past. Some of the most energetic events in the universe are driven by this process. When a supermassive black hole accretes matter at a very high rate, the energy released can be channeled into enormous jets of plasma that extend outward from the galactic nucleus at nearly the speed of light, reaching far beyond the visible boundaries of the galaxy itself. These jets are among the most energetic sustained phenomena in the known universe. They carry enough energy to heat the intergalactic gas in an entire galaxy cluster, suppressing star formation across the entire cluster environment. The phenomenon, called AGN feedback, for active galactic nucleus feedback, is now understood to play a crucial role in regulating the growth of galaxies. Without it, galaxies in rich clusters would continue forming stars far longer than they actually do. The jets from the central black hole of a galaxy like IC 1101 effectively shut down the star-forming potential of the surrounding environment. The black hole that built the galaxy also ultimately arrested its growth. Estimating the mass of the black hole at IC 111's center precisely is not possible with current technology. The galaxy is too distant and the core too obscured by intervening material for direct measurements of stellar or gas orbital velocities close to the event horizon. Current estimates place IC 1101's central black hole somewhere between 40 billion and 100 billion times the mass of the Sun. To put that in context, the black hole at the center of our own Milky Way, Sagittarius A, has a mass of approximately 4 million solar masses. The black hole at the center of the Andromeda galaxy is considerably larger, at roughly 100 million solar masses. The black hole at the center of M87, the first black hole ever to be directly imaged by the Event Horizon Telescope in 2019, weighs approximately 6.5 billion solar masses. The image of its shadow, a glowing ring of hot gas surrounding a region of darkness, became one of the most reproduced scientific photographs of the 21st century. IC 1101's black hole, at its lower estimated bound, is still 6 times more massive than that. At its upper bound, it is more than 15 times more massive. It is a black hole so large that the solar system would fit within it with room to spare. That range is wide, and the width matters for a specific reason. A competing candidate for the title of most massive known black hole is the quasar Ton 618, a luminous object located roughly 10.4 billion light-years from Earth. Ton 618 is not a galaxy in the conventional sense. It is the intensely bright nucleus of a galaxy in the early universe, observed as it appeared when the universe was less than 3 billion years old, blazing with the energy of matter falling into a black hole at a colossal rate. Its mass has been measured at approximately 66 billion solar masses, with considerably higher precision than the estimate for IC 111's black hole. If IC 1101's central black hole sits toward the lower end of its estimated range, Ton 683 retains the record. If it sits toward the upper end, the comparison becomes less clear. Some theoretical models propose a natural ceiling for black hole growth, roughly 50 billion solar masses, beyond which the accretion disk becomes unstable, so intensely irradiated by the black hole's own emission that the radiation pressure overcomes gravity and the disk disperses. Both Ton 608 and the upper estimates for IC 1101's black hole challenge that boundary. Whether the boundary is real or whether these objects represent exceptions to a rule that still needs refining is an open question. What is not in question is that whatever sits at the heart of IC 1101 is among the most gravitationally dominant objects we have ever inferred the existence of. It will continue consuming its surroundings for billions of years, not in spectacular bursts, but in a steady, patient consumption that will outlast every star in the galaxy by an almost incomprehensible margin. And they will fade. IC 1101 is classified not just as a giant elliptical galaxy, but as a dying one. Its star-forming era is effectively over. The reservoir of cold gas that once fueled the birth of new stellar generations has largely been depleted through billions of years of mergers, starbursts, and the relentless consumption of material by the central black hole. New stars still occasionally ignite in isolated pockets where residual gas has managed to cool and collapse, but they are vastly outnumbered by stars evolving off the main sequence, swelling into red giants, expelling their outer layers into space, and leaving behind the cold, dense stellar remnants that represent the final products of stellar evolution. White dwarfs, the dense Earth-sized cores of stars like our Sun slowly radiating their stored heat over billions of years. Neutron stars, the collapsed cores of more massive stars, compressed to the density of an atomic nucleus, spinning dozens or hundreds of times per second, radiating beams of radio waves that sweep across space like cosmic lighthouses, stellar mass black holes, the remnants of the most massive stars, points of no return around which the equations of general relativity apply in their full uncompromising form. All of these objects are accumulating in ES 1101. All of them are the inheritance of a star-forming history that has largely ended. The aggregate stellar population is declining. The galaxy is growing dimmer. It will not end in any spectacular catastrophe. Galaxies do not die the way stars die. There will be no explosion, no collapse, no final burst of light visible across the universe. What will happen is subtler and in some ways more final. Stars will age and cool. The central black hole will eventually exhaust its readily available supply of infalling matter. Not immediately, but over time scales far exceeding the current age of the universe, and the active nucleus will gradually go quiet. The galaxy's outer regions, already thinly populated, will gradually lose stars to gravitational ejection, scattered into intergalactic space by the cumulative effects of close stellar encounters over billions of years. What remains after timescales longer than the current age of the universe will be a diffuse halo of stellar remnants orbiting a central supermassive black hole in an increasingly empty region of space. The geometry of a galaxy will persist long after the light of its stars has gone out. Eventually, even the stellar remnants will not be permanent. On timescales of roughly 10 to the 34th power years, a number so large, it makes the current age of the universe seem like a brief prologue. Protons themselves may decay if certain extensions to the standard model of particle physics are correct. The white dwarfs and neutron stars would dissolve into their constituent particles, leaving only the black holes and a diffuse sea of elementary particles. The black holes themselves would eventually evaporate through Hawking radiation, a quantum mechanical process by which black holes slowly lose mass by radiating energy at a rate inversely proportional to their mass. The most massive black holes, those like the one at the center of IC 1101, would take the longest to evaporate, persisting for timescales on the order of 10 to the 99th power years, but they too would eventually disappear. IC 0001 will fade from view not by any dramatic event, but by the gradual irreversible dimming of 100 trillion fires burning down, and then the slow dissolution of everything those fires left behind. When we consider the fate of IC 101, it is worth noting something about the nature of galactic collisions that makes this endpoint particularly significant. When galaxies merge, the stars within them largely survive intact. The distances between them are too great for direct collisions to be common. A star that formed in a dwarf galaxy 11 billion years ago that survived through multiple mergers as its parent galaxy was absorbed into progressively larger structures might still be burning today inside IC 1101. The history of those mergers is not erased, it is incorporated. Every layer of IC 1101's current size represents a galaxy or 100 galaxies or 1,000 that once existed independently and now contribute their stars to the total. The distinct identity of each ancestor galaxy has been lost. The stars remain. Ixilvan Blok Un is in a sense an archive of the cosmic history of its corner of the universe. Every galaxy it has consumed, preserved in the collective stellar population of the whole. Their individual stories absorbed into a single enormous story that is still unfolding. The scale of that archive is difficult to hold. 100 trillion stars. Many of those stars are old enough to have formed and evolved entirely before the Sun existed. Some of them may have had planets. Some of those planets may have developed chemistry. A tiny fraction may have developed biology. An even tinier fraction may have developed intelligence. And any intelligent life that emerged in the early history of IC 1101 in the first few billion years of the galaxy's existence, when it was smaller and still actively forming stars, has had an inconceivably long time to develop. If civilizations arise and persist in IC 1111, the way they appear to have arisen on Earth, then the oldest civilizations within that galaxy may be billions of years more advanced than anything we can imagine from the vantage point of 2025. The arithmetic of deep time applied to a galaxy this large and this old produces implications so extreme that they are genuinely difficult to take seriously as estimates. But the arithmetic is straightforward. Whether its conclusions are realistic depends entirely on assumptions we cannot yet evaluate. Our observable universe is estimated to represent only about a quarter of the full extent of everything that exists. What lies beyond the cosmic horizon, beyond the boundaries set by the finite speed of light and the finite age of the universe, is entirely unknown to us and may remain unknown forever. The light from those regions has not yet had time to reach us. Some of it may never reach us, as the expansion of space carries distant regions away faster than light can cross the growing gap. The designation of IC 1101 as the largest known galaxy applies only within the survey area we can access, which is a significant but ultimately partial view of a larger whole. This limitation cuts in two directions. It means we cannot say that IC 1101 is truly the largest galaxy that exists, only that it is the largest we have found. But it also means that if a galaxy this extreme is found within the quarter of the universe visible to us, the full distribution of galactic structures across the whole must contain many others like it, and possibly some larger still. The universe, as best we understand it, does not arrange its contents with any special consideration for the particular vantage point of a small planet in an average galaxy. The observable universe is almost certainly a fair statistical sample of the whole. If IC 1101 is 101, sits near the upper limit of what a galaxy can become, then the unobservable universe contains many galaxies near that same upper limit. If there is no upper limit, if the process of hierarchical merger can produce structures indefinitely larger than IC 1101 given sufficient time and gravitational resources, then the unobservable universe may contain structures that would make IC 1101 appear modest. We have no way of knowing. What we can do is recognize what IC 111 tells us about the universe within our reach. That the upper end of the distribution of galactic sizes is far more extreme than the typical size might suggest, that galaxy formation is a process capable of producing objects of almost incomprehensible scale, and that the forces driving that process, gravity, time, the hierarchical clustering of matter along the scaffolding of the cosmic web, operate without any apparent ceiling. We do not know if there is a theoretical maximum size for a galaxy. There may not be. As long as matter exists and gravity operates, mergers can continue. But the expansion of the universe imposes a practical constraint. As space expands, galaxy clusters that are not gravitationally bound to each other recede from one another at increasing speed, driven by the dark energy that makes up roughly 68% of the universe's total energy content. Dark energy appears to function as a property of space itself, a repulsive pressure built into the fabric of the cosmos that counteracts gravity at large enough scales. On scales smaller than galaxy clusters, gravity wins, bound structures hold together and continue to evolve. On scales larger than clusters, dark energy wins, the universe expands, and the unbound regions of space grow ever more distant from each other. The pool of potential merger partners for IC101 is therefore finite, and it is shrinking with time. The galaxies within Abell 2029 that have not yet been consumed will eventually be, or will be gravitationally ejected by the same encounters that could have drawn them in. The galaxies in neighboring clusters will recede until they are unreachable. The raw material for further growth is running out. Ich noise has had 11 billion years and the gravitational resources of one of the richest clusters in the observable universe to work with. That has been enough to produce something without equal in the observable universe. Whatever comes next for it will not be growth, it will be the long, gradual quieting of everything it has built. It is old, it is dying, and it is the largest thing of its kind we have ever seen. It was ancient before the earth formed. It was already in decline when the first animals appeared in our oceans. It will outlast the sun by a margin so large that the entire history of life on Earth is a rounding error by comparison. It was always going to outlast us. Not because we are fragile, though we are, but because the time scales on which galactic objects operate are simply of a different order than the time scales on which biological and even planetary processes occur. The universe is not indifferent to us because it is hostile. It is indifferent to us because it operates at scales so different from ours that our entire existence, from the first cell to the last star we will ever see, is effectively instantaneous by comparison to the processes that produce and consume things like IC1101. And yet we are here, and we can observe it, and we can measure it, and we can ask questions about it. That is not nothing. Whatever IC1101 contains, whatever worlds orbit its 100 trillion stars, whatever histories have unfolded within its span, we will never know directly. The distance is too great. The light travel time alone means we are seeing it as it was a billion years ago, before the solar system existed. Any signal sent from within IC1101 toward us today will not arrive for another billion years, long after the Sun has evolved off the main sequence and the Earth, in all likelihood, has ceased to support the kind of life capable of receiving it. IC1101 is as close to truly unknowable as an observable object can be. It sits at the edge of reach, visible enough to study in outline, too distant to study in detail, and too large to hold in mind all at once. We can measure its size and approximate its age. We can infer the mass of its central black hole and estimate the temperature and metallicity of its stars. We can classify its morphology and determine its place in the large-scale structure of the universe. What we cannot do is know it. The difference between measuring a thing and knowing it is the difference between a map and a territory. And in the case of IC1101, the territory is larger than anything else we have ever tried to map. We found it by accident. We recognized it slowly. We misidentified it for over a century. We are still working out what it means. And it is very possible that we have not yet asked the most important questions about it, that the questions which will eventually matter most are ones we do not yet have the conceptual vocabulary to formulate. That is the particular condition of a young science looking at an old universe. IC1101 has been there for 11 billion years. We have known what it was for barely 30. In the time it took us to recognize the largest galaxy in the observable universe for what it is, IC 1101 has barely perceptibly aged. The universe is patient. We are the ones running out of time.